Hello guys, here's Konstantin from Moscow, Russia. I am a Raku and Ethereum enthusiast with a long Perl background. I am maintaining and contributing a few modules, also previously have taken part at some Perl, Raku and open source related events. Anyway, today I'm in Raku development room at FOSDEM 22 and it's first FOSDEM with explicit Raku space. So for me it's very great and impressive. Well, today I will share a short sample of common Ethereum and Raku usage. I name it Decentralized Authentication. Hope you'll find it interesting and maybe will use at some of your project. So let's start. In the beginning, I would like to speak about the evolution of authenticators. Traditionally, the authenticator was integrated right into the application. It's the case of Web 1.0. The user had to register and then, using a login and a unique password, enter the personal account, post the commands, download the files, or doing whatever he wants. Credentials were stored on the web application server, and the flow of authentication, authorization, and identification was managed by some module or service. This is the sample of hyper-centralized authentication. Next, built-in authenticators have been evolved to the external third-party authenticators. In the era of global services and social network like Web 2.0, the visitors as well as site owners began to delegate authentication to corporations. At the backside of that process, we have got a bloom of phishing sites and explicit target ads. In addition, there were clear symptoms of centralization and de-anonymization. And finally, blockchain, it's the Web 3.0, has naturally become the third iteration in the evolution of authenticators. On the one hand, the technology provides a truly decentralized and transparent audit platform for authentication, and on the other hand, it makes the authentication and identification flow much more anonymous. The configuration of Ethereum node could really boost the authenticator options and features. For example, we can set up the non-sealer node, disable unlock account, or disable outgoing transactions at all. Combination of these settings allows to get the listener node with blockchain read-only permissions. It means we can get the permission levels for authenticators as nodes within one network. I will consider Proof of Authority Consensus Network as a target network for authentication. POA networks uses a set of authorities, the nodes that are explicitly allowed to create new blocks. So the chain has to be synced off by a majority of them. The general advantages of the POA consensus network are, of course, it's a secure network. It's lightweight, I mean mining does not require lots of computation as compared with a proof of work consensus. Its performance, high performance network with high performance, and has high predictability and high flexibility. Deployments are used by enterprise and by public. For example, you can deploy it to the public Gerlo network or Robson or other public network. You only have to authenticate your identification from web application at any node in POA network, and your identity session is saved on blockchain. While you're interacting with the web application, your session is updating explicitly or in the background. You can share the authenticator smart contract address with Identity Trust Fabric. The Identity Trust Fabric and its supporting infrastructure, I mean network, exchange protocol, services and interfaces, acts as a third party between the web application and external service providers, handling the identification and access requests. So since your identity session is validated, you can get access to all services provided by this fabric. Authenticator software could be classified as on-chain and off-chain. Actually, it's the whole software model. Looks simple. But one note, on-chain and off-chain components work together, but obviously are independent and interact with a third-party provider, Ethereum node client. This is software that verifies all transactions in each block, keeping the Ethereum node secure and the data accurate. Many Ethereum clients exist in a variety of programming languages such as Go, Rust, Java, and others. The common thing, they all follow a formal Ethereum yellow paper, and in other words, it's Ethereum specification. On-chain software is a smart contract. The Ethereum blockchain is essentially a transitional singleton machine with shared state. Transactions are processed by own Turing-complete virtual machine, known as Ethereum virtual machine. The EVM has own bytecode. Programmer writes a program, smart contract, in a high-level language like a Solidity. Then the program should be compiled down to bytecode and committed to the Ethereum network as a new transaction. Off-chain software are backend and frontend. Backend interacts with Ethereum node client software via RPC or IPC, inter-process communication. To put it simply, backend delivers the next generic features. First of all, it's account unlocking. The next, deploy an Authenticator smart contract to Ethereum network for every unlock. And the third one is interacting with the smart contract functions, validation, update, closure, and other things that your contract can provide. On the other side, backend responses the data to render in web application by frontend, but we will consider this later. Okay, in this picture, it's me explaining you the trivial authenticator algorithm. So we are entering into algorithm section. So I will open GitLab and show the block diagram for the first trivial authenticator. Okay, it's loading. Seems to be loaded. Yeah, nice. What is the most important things here? First, we have two major master groups. Authentication and session management. The next thing, we have two blocks with a pink background. Here and here. Actually, we have irregular blocks with a gray and the green background, but pink blocks means the write operation blockchain, and as write operation is quite slow, it's about 1 second per operation on fast public networks, so you can estimate the edge performance. Each group will take at least 1 second, and full path through this algorithm will take at least 2 seconds. Authentication group is simple. We send the address and password from Prolog, these nodes, its login form, and post other password pair via admin road. Then it tries to sign this message on node with these credentials. If everything went well, we got the address authenticated, and in the end we deploy the Authenticator smart contract, and voila, the session is started. Here is a deployment node. Then we have to collect some metadata from newly deployed contract here, and then we pack these details into the cookie and send to frontend. Let's consider the session management group. It's a little bit complicated. The input is the transaction hash from previous operation. As we discussed, on previous step, we can deploy the smart contract or we can update the session. Anyway, we try to retrieve transaction details from the blockchain. In terms of Ethereum, it means to get the transaction receipt. By the transaction details, we can get some contract deployment address. We can get smart contract deployment address, and get it logs. The logs or event associated with this contract. This data is used to check the session and make the decision about its validity. For example, here we get the address of smart contract, here we collect the logs, here we check the session, and if it's okay, we update the state of the smart contract. If everything went well, and on the step also we got the session updated, and it means that the session is valid for a while in the future. So if update went so, contract still active, we perform the actual update, then got the metadata from new updated contract and pack it into the new cookie and send the cookie to frontend and wait for a new request from admin layer. So it's simple. So let's get back to the presentation. Okay, next slide, and this is a picture is like I keep calm and explain it once more. So let's go back to the GitLab. Here's a new algorithm. And the update for trivial algo is Authenticator with the balances. It's totally based on the trivial version, but improves it with some tricky specific to blockchain steps. First, as you see, we have a few pink nodes more. For example, here we have 2 nodes, and here we have also 2 nodes. So that's a bad news, because we have new delays and new latencies. But let's see what's happening there. At auth group, we have some blocks for calculating the random amount in Pheix. For example, here this block is Pheix is the smallest denomination of Ether, Ethereum cryptocurrency. And this random amount is calculated on Backend. It's very important because it's strong enough against the random calculate on a smart contract that we will discuss in a little bit below. Then we send this amount to the smart contract address and at the same time attach this amount as encrypted data to the sending transaction. Sounds a little bit complicated, but the idea is to check this amount at session management group. I mean here. In other words, how trivial algo works. We just get the receipt from transaction and validate the session. If OK, we update the state. But here we also have to check the amounts. This check has a few steps. We got data from the transaction, decrypt it and check it both on smart contract and account sides. If everywhere the amount is equal, it means that no third party was in the middle and the session is fully validated in blockchain. One thing we should keep eye on is how to securely store the private key for encryption, decryption and backend, but I think it's a task for administrators. So as you see, we got the details, try to update the balance, check account balance. If it's okay, generate new random amount in Pheix, update the public key or any metadata inside the smart contract, calculate and encrypt balance, send it to smart contract, and return the transaction as a hash. And then wait for a new request from the admin layer, I mean from the front end. Okay, let's go back to the presentation. Let's consider a few attack vectors for these algorithms. As we know, smart contracts are deterministic, so basically every functions are predictable. If we know input, we will be and we should be know output. And you cannot get random number without any input. Almost every language generates set a random number using the clocks. This means you will not get random number in blockchain using a simple method. You still can make another smart contract with the same logic executed on the same transaction, and you will be knowing what random number was given at origin smart contract. Authenticator smart contract is time dependent also. This creates an opportunity for the miners to reduce or increase session time frame due to some freedom in setting a timestamp for a block. This is especially noticeable when timestamps or block hashes are used as a source of randomness. It's just our case when we try to generate some private or public key on a smart contract. On the other side, since the authenticator smart contract is deployed to public network, denial of Ethereum takes pool services attack could be applied. An attacker can manipulate the transactions to authenticator smart contract address, stack them, for example, in pending status. And as the session time frame is sensitive to timestamps, any synthetic delay or latency like pending status on transaction due to attack could break the authentication logic. And of course, on the other side, since the authenticator smart contract is deployed to private network, the auth session details could be used to compromise this network. An attacker potentially can find out the number of blocks in a private blockchain, get the ceiling block period, get block difficulty and other network parameters. These parameters could be used for the attacks on your private network, so you should keep it in mind. Let's discuss the generic smart contract for Authenticator. It has a few basic functions like an update state and get PK, I mean some public metadata. This is code in Solidity. As you see, we have public and only node owner pragmas for the smart contract. Oh, sorry. So going to the corner. Okay, this function have important property. They could be only called by contract owner. As I said, we have a public only owner pragma here, and the logic is quite straightforward. Owner deploys the smart contract to the Ethereum network and operates with it. Any access to smart contract function or data from non-owners is denied. Also, please notice that the source code of this smart contract is available via this link, so keep free to check it out, review, or doing whatever you want with this code. And let's discuss why we have a weak randomizer on smart contract. As I said before, trivial authenticator operates with timestamps. We have a global mutable variable timestamp where the last block timestamp is stored on every write access to the smart contract. Also, we have a current latest block timestamp available from our code. The difference between these timestamp is the session time frame. On every update, the trivial authenticator compares the actual session time frame length with the origin one that was passed to constructor from the backend on deployment. If the actual time frame is higher, the origin one smart contract self-destructs and no longer available for use. Session is set to closed. So on the slide also I show that getPK function use getPseudorand to generate some metadata, and this pseudorand function relies on block difficulty, block coinbase, block gas limit, block number, and block timestamp, exactly that parameter that could be compromised by miners and could be attacked by some could be corrupted by some kind of attacks that we discussed before. We can do this random seed from the getPseudorand function a little bit safer if we pass some random seed to constructor from backend on every deployment. So it makes things better, but actually you should use randomizing functionality on smart contract side carefully. Backend is completely written in Raku. I used Pheix content management system as a prototype. On one hand, it's the only CMS with Ethereum blockchain native support. On the other, it's well scalable and extendable via the modules and add-ons. Pheix is based on concept of hybrid CMS. It works as a legacy CMS while global templating rendering, and as a headless CMS while fetching content from each page where there's asynchronous IP requests. From the perspective of front-end, the backend is truly headless. The front-end in JavaScript is JavaScript application and works directly in browser. Once the general page template is loaded, a content is retrieving via API and rendering will write JavaScript components library. Pheix has built-in API debugger, the link on this slide, and you can check it with a simple request and see what responses the backend gives to you. Here's a sample request. It's JSON with two major keys like a route and credentials. Method key is just for route optimization. We can use single route for different methods like a get, post, or for instance patch. The response also quite straightforward. We have a mandatory field like status, render time, message, but at this response please look at content t-params and content component. Component base 64 encoded HTML template to be rendered via Riot.js library at frontend, and the t-params is the collection of variables to be replaced. So here you see the header variable with a welcome message. So if we decode the component, we see the plain HTML with a placeholder props header, and here the variable will be rendered. So we see welcome in the header. Content at this component could be responsive. You can add additional render logic, integrate third-party JavaScript extension, and introduce specific handlers for t-params collection. It was really handy during the admin panel front-end application implementation. Also, here is a link to the real-time example, so you can check how it's rendering in browser and what's happening under the hood. During the usual foreground session, the updates on the server side like cookies, success tokens, passport, whatever, are applying on client demand. Client clicks the some link, action passes through the one of administrative layer routes, and default session handler validates the request and updates session environment. The blockchain authenticators eventually support the foreground sessions. But since the blockchain write operations are quite slow, the client will get the additional latency about 3 seconds on every request to administrative layer. So to prevent this latency, shadow sessions are introduced. The idea is to absolutely straightforward. Frontend traces the session with an asynchronous background request to blockchain and tries to update session before its expiration in background. In summary, clients notices no delays and get session with auto prolongation. On the other hand, the shadow sessions are less secure against the traditional foreground sessions. The methods to enforce security is, for example, trace page scrolling on mouse activity. If no activity, we should skip auto prolongation. Or we can simply mix foreground session and background session. User will experience the latencies, but not on every request, so it will be a little bit less annoying. So the sample modular routes are presented on this slide. Before we should add our modular to the Pheix, we should configure it. We should specify the generic routes. First of all, there should be a default route for initial entry point. There should be, of course, authentication route for initial authentication on the node and set up the session environment. It's our admin auth route. And finally, we got a session validation route for validating the sessions. Pheix uses route-to-write templating and routing engine. It's quite reactive and fast. You can find this modular at Raku ecosystem, and maybe you can try it in your own projects. Here is the config file, JSON config file for the routes. As you see, we have 3 entries there. Every entry is for exact route. For example, default route, authentication route, validation route. Each entry has a path, and each entry has a reference to the API method that should be used for handling this route. Just to add modular to the global, to integrate the modular to the Pheix, I mean, Pheix should know that new modular is available to use, and you just need to add the modular to global Pheix config file. You should add the new entry with the package name. Of course, it should be unique in the namespace of Pheix modulars, and also you should use the unique key identifier for this package. Also, we have specific methods required by Pheix. 4 are not very important. For example, getClass, getName, getSM, and getSeoData are the methods that are used to search engine optimization. And for now, you can just keep them as bulks or gaps with no algorithm inside. Init.json config method is really handy. It initialized their own modular config, so yeah, we should use it. And get method is just some kind of update on the default controller. We pass the default controller as an argument, and if we need to modify or set some properties of this controller, we use get and return back the controller to the caller. So eventually you should integrate this. You should implement these methods in your modular, and yes, without these, integration will be inconsistent. General Authenticator Logic, I mean trivial authenticator algorithm, is provided by auth API and ses API methods. To be honest, these methods are just mostly wrappers over the auth on blockchain, validate on blockchain, and session detail methods. Auth on blockchain is just implementation of authentication group from trivial algo. Validate on blockchain, it's an implementation of session management group from the trivial algo. And session details is a helper that used to import details, import session environment details. Also, this method calculates session expiration time and return expired status a little bit earlier before actual expiration, just to reserve a short time slot for foreground session update. This is configurable setting, and it has sense only for short sessions, where average client idling period is close to the session time frame. For long session, it could be switched off and has no any sense. The general idea of cache contract feature, we use a client address to find out active authenticator smart contract. This feature is secure enough because functions of smart contract are available only for owner. This feature is made the smart contract recyclable. So if the smart contract is active, a client can authenticate with it once again and no redeployment required. So this boosts performance at initial authentication step. And also cache contract feature depends on authenticator smart contract ability to emit events in constructor. So our contract has such ability, so it simply used there. The cache contract feature should be integrated to trivial authenticator section right before the deployment authenticator smart contract call. Just a few notes on this slide. We just need to get latest deployed smart contract, get latest update state for this get latest transaction, update state transaction for this smart contract, and try to validate with this transaction. Let's see how it looks at the algorithm. It's a trivial algorithm. Yes, we need to add these fields, these nodes before they deploy authenticator smart contract. And if we can validate the previously deployed smart contract, we use it. If no, we deploy the new one. Ethereum node client provides a flexible mechanism to filter events. It's available via JSON RPC for backend and via JavaScript console for administrator. I mean Ethereum node administrators. Well, here I will use JS console. This code snippet is used to get the authenticator smart contract and deployment transactions. After execution, the current filter res variable will contain array with the smart contract details. These events are filtering by event ID, and in the snippet, as you see, we have one for filter smart contract deployments and two should be used to filter update state transactions. So let's see the result of filtering. On this listening filtering results are presented. The important notices are triple dots are used just for hashing shortening. Every hash is 64 characters long, so it's tricky to fit it on the slide. And also we should keep an eye on data in topics. It's the most important. There are event signature and event ID. Here is the signature and here is the ID. ID is just one with a leading 64-0. It's the result of the padlef function. So yeah, the goal is to find target transaction hashes. In the snippet, they are the values of the transaction hash key. So for every entry, we got the transaction and we try to authenticate user with this transaction. So it's quite easy. Authenticator on public Ethereum network could be useful for the cases while you are building open, transparent, and traceable authentication flow for independent application or systems. Since we use public network, all data is available for third parties. From one side, it's data leakage. Attacker or fraud can see who is currently authenticated on public authenticator, how many authentication sessions were opened, and when will the current session be closed for some address. Seems really unsafe, but from other side, smart contract knows nothing about the application it's interacting with. Doesn't store any details except of timestamp and public case or metadata, so it looks quite anonymous. But we can share the public key for Ethereum address with the backend, and voila, backend can submit signed transaction and actually works as extremely trivial Ethereum client. We just have to care how to keep private key securely. For example, add some lock-unlock mechanism and update trivial authenticator algorithm. In this slide, we just have to switch try to authenticate block to private unlock key, and then deploy smart contract deployment block should be switch it to the call Authenticator smart contract for update or self-destruct. This means we have pre-deployed universal smart contract that should be used to remote authentication for signed transactions for users addresses that use signed transactions. Okay, I will go through. I will do a quick overview of native administrative layer concepts. Okay, I use Pheix, as I said before, it's artistic 2.0 lessons completed throughout Raku-driven content management system with data storing on blockchain, extremely lightweight, reactive, and scalable, blah, 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 blah. One thing we should mention about its official beta version now, and I will bump the version to release candidate in this March. BlockPheix.org was opened in the middle of 2020, right before the Pearl conference in the cloud. And since the start, it collects access statistics and saves the crash logs for itself. Usually, I'm just checking them via server console with some dummy bash, some not dummy, but some weird bash comments like, here I got a file, pipelined it to Perl with some regular expression, and finally got the details about the statistic for January 23. Here is the output. It daily accessed by country. The results are presented as date and country separated by vertical bar. Very easy and more or less human readable. The crash logs, much more complicated. They use log entries are base 64 encoded. So we have to use another command a little bit longer just to cut the logs and pipelined into the Perl command with some additional modules. But finally, logs looks quite good. We have separators in different colors. We have a date timestamp in different colors, so it's quite readable. But I would like to say that I'm quite lazy to prompt this command every time, and I've started to think about native administrative panel, just for fun or quick logs and statistic checking. As the Pheix is declared at same as on blockchain, let's introduce authentication on blockchain for admin layer. So now I will show how it works. I need to do a quick setup. First of all, I open the VPN to my blockchain nodes. Yes, it's opened. Let's connect to the server. Yes, we're here. Let's see that Docker is running. Yes, status is okay. Now let's connect to the server with the Pheix block. Yes, we're there. Let's open screen. Here we should to forward the secure tunnel to the Ethereum node server. It will be something like this. Yes, it's opened. A new one console. Yes, we're there. Now we check that it works. Yes, we got the response from the node on our web server, I mean public server. So for now, let's go back to the presentation. Here's the Pheix.org site, and let's go to admin road. Yeah, we got the login form. Let's check what account address should be used for login. Yeah. Let's try some password, incorrect password, I mean. Yeah, nothing happens and the password is not right. And now we try to apply the correct password. Yeah, it's a little bit long because for now we are deploying the smart contract to the blockchain. So it takes a few seconds. Let's see what's happening. Yes, we are successfully authenticated. This is the main page. Here we have a metadata or private key, as I said before. Also, we have a transaction hash as a token. It's a deployment transaction. Let's see what's inside the admin panel. Yes, we can go through our crash logs. Let's see what's there. Yeah, now as you see we have a few ones. The latest was on January 30. Some IP requests were failed. And also we have a traffic diagram. Let's see what there. Yes, we got the, as you see, we got the session update in foreground. We have, as I said, we have a little slot for foreground updating sessions, so that this query takes a little bit longer. But here we have a plot. Yes, we have this peak. It was on January 27, 40 visitors. Yes, something like this. And now I will just show you how the session updates in the background. As you see here, we open the console. Yeah. And you see it will send the request in background to the backend. Yeah, new request is sent and the session will update. Just notice that the timer will reset. Yes, it's done. Okay, let's go back to our presentation. Yet another way to make things better, I think we have a few open points. As we discussed at the features section, we have a catch content feature, but for now it's unfortunately fully unimplemented, so I'm planning to deliver it in future in RC1 release. We have no exit feature for closing sessions. And also we have to modify generic roads for administrative layer. As we discussed at the section, we have a few roads, just auth and SES roads, but we should add some new ones like a validate, prolong, and close. If this update impacts some authenticator model structure, it should refactor and update methods in subclasses, and also algo should be slightly changed. And after this, we can say that we have auth engine on Ethereum node. So yeah. I would like to invite you to Pheix development process. Code review, forks, and merge requests are very welcome. Here's a link to official repository. Feel free to join the Matrix workspace for any question and feedback. And if you want, you can check my profile at modules.raku.org. There are a few modules that I'm contributing and maintaining. Maybe you can find them interesting. Also, I'm inviting you to the development process. If you want, you can support me. Just make a small donation. The details are on Pheix.org blog. So yeah, it's finished. I would like to thank you for your attention. I would like personally to thank Andrew for organizing and managing this room. Of course, I would like to thank all FOSDEM orgs and Raku community members. Yeah, thank you very much. I hope you found something useful, interesting in my presentation, and of course, any feedback, suggestions, subjections, everything is welcome. Please go on. Thank you, and see you later.